Hello, algebra students. I think I'm recording. This is my MacBook. My other computer was time to put it out of its misery. So I hope I'm doing this well. I hope it's turning out okay. This is going to be on probability, and probability is all going to start with the fundamental counting principle. Now, let me ask you this. Let's say you had 3 different shirts to wear. 3 shirts and 4 different pairs of pants. Okay? And I'll tell you what, to appease those shoe lovers in the crowd, let's give you 5 pairs of shoes. How many different outfits could you make? Well, let's assume an outfit includes 1 shirt, 1 pair of pants, and 1 pair of shoes. Now, I know some of you with rather attractive feet could go barefoot and say that's an outfit too. Well, maybe so, but we're going to keep it to 3 shirts, 4 pairs of pants, and 5 pairs of shoes. Vinny, that doesn't mean you can take your shirt off and assume that, hey, I got a cool outfit here, because I realize how buff you are and all that, but never mind. All right, let's get on task. How many different outfits can you make? Well, back in like 5th grade or 6th grade, you would have made a tree out of this. And you would have maybe a red shirt, a blue shirt, and maybe a green shirt. And then you would have built your pants off of that. Like, you got your jeans, and then you got your, your dress pants, and then you maybe got some corduroy, and then maybe some basketball pants. And then off each one of those, you would have built your shoes. You got your high tops, and then you got your, your running shoes. Okay, you got some boat shoes or loafers, right? And you would add 2 more things. And man, that really, look at the mess it's making already. I don't want to do it that way. But thank goodness I don't have to. Thanks to the fundamental counting principle, I can just say 3 times 4 times 5. And that's going to be 60 different outfits, assuming that each outfit consists of 1 pair or 1 shirt, 1 pair of pants, and 1 pair of shoes. Pretty simple stuff. The fundamental counting principle tells me that if something happens m ways, something else happens n ways, then together they happen m times n ways. Well, let's take a look at it. Let's say we were going to flip a coin and roll a die, which is singular for dice if you don't know that. Flip a coin and roll a die. All right. Well, how many outcomes does flipping a coin have? 2, heads or tails, right? Well, in a die, we're assuming a 6-sided die has 6 different outcomes. Well, together, they have 12 different outcomes. Yeah, 6 times 2 is 12. It's that simple. If you really wanted to, if you didn't believe me, you could make a little table here. You could go heads or tails. And then if you get a head, you might get a 1, 2, 3, 4, 5, or 6. And then, of course, if you get a tail, you might get a 1, 2, 3, 4, 5, or 6. The way I'm reading this is heads in a 1, heads in a 2, heads in a 3, heads in a 4, heads in a 5, heads in a 6. All right, and then tail 1, tail 2, tail 3, etc. So you see there are 12 different outcomes. So if you go out to dinner and you have a choice of 4 soups, okay, maybe 2 different salads, all right, 6 appetizers, 5 entrees, and let's go 6 desserts. How many different meals can you make that consist of soup, a salad, 1 of the appetizers, 1 entree, and 6 desserts? That'd be a pretty big meal. Yes, indeed it would. Well, you're just going to go 4 times 2 times 6 times 5 times 6. And I know I got 6 times 6 is 36. There's an 8. 8 times 5 is 40. So I've got 36 times 40, right? And so we're going to get 0. We have 24 and 3 is 7. Carry the 2. 12 and 2 is 14. There should be 1,470 different meals you could make, all from the fundamental counting principle. Okay, now a good lesson for you is don't look to add, look to multiply. Now let's try it this way. Let's say you're going to take a true-false test, and there's going to be 8 true-false questions on this test. 8 true-false questions. How many different ways can you answer it? Well, some of you are going to go 8 times 2, 16. No way, you're not thinking. Question number 1 has 2 possible outcomes, doesn't it? Question 2 also has 2 outcomes. Questions 3, 4, 5, 6, 7, and 8 all have 2 different outcomes, right? Well, I multiplied the outcomes together. So the number of different outcomes would be 2 times 2 times 2. Oh my gosh, 5, 6, 7, 8, or better yet, 2 to the 8th power, which I think is 256. Let me see, 2 to the 6th is 64, which means 2 to the 7th is 128. Yeah, 2 to the 8th is going to be 256 outcomes. Of course, if you're trying to get a perfect on this, only one of those outcomes would get you a perfect score. Now, you miss one, you get about an 87.5%. That's not too bad. There'll be a lot that have those, but 256 total outcomes. What would happen if you were taking a multiple choice test? Maybe there's 5 questions. 1, 2, 3, 4, and 5. And they were each A through C. A, B, C. Okay, each one had those 3 choices. So let me see here. Okay. Just like that. All right, well, if I'm following what I said before, each question has 3 outcomes, and there's 5 questions, 3 to the 5th power. I know 3 to the 4th is 81, 3 to the 5th must be 243 different outcomes. Yeah, way more than you thought. What if you're taking a mixed test? And let's say there's 7 true-false questions, and there are 3 multiple choice, A through D. Okay, well, the 7 true-false, there's 2 to the 7th power, and this is going to be 4 choices to the 3rd power, right? Okay, well, 2 to the 7th, 128, right? 128. And 4 to the 3rd is 64. What do you think I should do with these 2 numbers? I should multiply them. So I should do 128 times 64. And you know what? If this is, you can go ahead and multiply that, but that's 2 to the 7th. And this is 2 to the 6th. Right? That's the same as 2 to the 6th. So it's 2 to the 13th power. Remember, like bases, multiplying, I add the exponents. Well, I know 2 to the 10th is 1024. 2 to the 11th would be 2048. 2 to the 12th, 4096. And 2 to the 13th is going to be 8,192, I think, if I do 4096 to 19. Yep, that's right. There you go. So altogether, there'll be 8,192 different ways to answer this test. There are 7 true-false questions and 3 multiple choice questions, A through D. Now, there's one more thing I want to tell you. We'll do part 2 of probability tomorrow night. But let me see, is that going to work? This is going to air Tuesday night, Wednesday? Yeah, that'll work good. Okay, one more thing is, in probability, you're going to see this symbol that looks like this, an exclamation mark. Okay, when you have a number in front of it like this, that is called 5 factorial. And what that means is 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, times 3 is 60, times 2 is 120. Okay, if I had 9 factorial, that'd be a pretty big number because I go 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, I could pick it up here, go 120, 720. I'm not going to multiply it all out. I can show you how to do that on your calculator. It's real easy. But I do want to point this out to you. What if I had 10 factorial and I was dividing by 7 factorial? Well, 10 factorial would be this, right? And 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, you know, Mr. Lawrence, I like to cancel out wherever I can. And since the numerator is all multiplication, the denominator is all multiplication, and there's division here because of the fraction bar, I can divide the 7s out, the 6s out, the 5s, the 4s, the 3s, the 2s, and the 1s. And so the problem becomes 9 times 8 is 72 times 10. This would equal 720. That is called factorial. Okay, factorial. All right, I think that's all I'm going to put in the video. We'll get some practice with this kind of stuff tomorrow, and then or in class. And then tomorrow night's video will be something about permutations and combinations, and that's really going to be it. I mean, that's going to be it. All right, Mr. Lawrence signing off. Have a good night, everybody.